Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 13. We have been discussing about the orbital elements. So, we will continue with that. So, for the two body system, we got the relative motion equation, and from thereafter we have been developing how the orbit will look like. So, we have already discussed that there are 6 parameters for that relative motion equation, the 6 constants of integral, and those constants of integrals we have written as A, E, the 6 constants of integrals, the 6 integral constants or 6 constants of integration we have written as A, E, small I, capital omega, small omega, and theta. This we have written as true anomaly. Omega as the argument of perigee, capital omega as the nodal angle, inclination of the orbit, and this is eccentricity, of the orbit, and this is semi major axis. So, if we discuss the case of Earth, so at the center of Earth we can place an inertial reference frame which is not rotating along with the Earth. Okay, and let us say this is x, y, and z, and this then constitutes the not the equatorial plane of the Earth, but the plane of the inertial reference frame, x y plane of the inertial reference frame. Okay. So, here this frame, this is non-rotating, but it is a being dragged along with the earth around the sun, and therefore, in reality this is not actually inertial in true sense. Like what is the difference? I will show you here. Say a block is hanged from the ceiling like this. So, if you push it, so this will have a purely translational motion. This will not have a rotational motion, because this block will, if it is pushed from one place to another place. So, this block will look like this. This position will come here and this will go here. So, this is a purely translational motion. In this, you can see that the orientation does not change. A line joining a line like this, it remains horizontal here itself. While in the rotational motion, what you will see that if I have a say here a circular chord or whatever it may be, it is a fixed with this. At this point it is a fixed, this point is non-rotating. So, here the card cannot rotate, but here in this place there is a pin, and about this it can rotate. So, then you can see that a line like this, if it is here, after some time if it gets displaced, so this line will appear like this. So, this line orientation initially was in this direction, now it is in this direction. So, this has rotated. So, this is a rotational motion, while this is purely a translational motion. So, similarly, here in this case, this reference frame x y z, okay, this is an inertial reference frame, and this is just rotating around the sun. Let us assume that the sun is, because we are writing equation with respect to the sun. Okay. So, this reference frame, if it is right now it is here in the orbit. So, after some time once it goes here, so still the same orientation will be maintained, the orientation will not change. Okay. So, all through the orientation remains same, but you can see that the center of this origin of this reference frame, this is accelerating toward the earth, toward the sun, okay, because it is going in a curvilinear path here in the elliptical orbit. So, in true sense this is not an inertial reference frame, but right now we can assume that this is equally valid, though this is not valid reference frame this way. Some corrections are need to be given to this kind of formulation, and there are many books related to this, how to give the corrections and taking the relativistic effect. There are so many things which can be discussed. So, one book on ephemeris, something if I remember correctly, this is by Siedelman. One book is there. In that book you will find all these details, okay. And there are many other books on astronomy which will give you this kind of how to do this correction, relativistic correction and other things, this acceleration. And but for the satellite around the earth, we can assume that the acceleration about the sun is so small that we can assume that we can safely assume that this translating reference frame, it is serving as good as an inertial reference frame. This is translating and accelerating. Okay. So, around the earth, our satellite, it goes like this. So, this is the orbit of the earth, satellite around the earth, and it will go like this. It will cross this plane, it will go inside this plane. So, this plane also I will make it here something like this. So, this will go inside the plane. So, inside the plane I will show it by dotted line, and from here, from the back it is coming, okay, going inside, it is coming like this and going inside this. Okay. Outside you can see it, it is a solid, inside here it is a dotted one. Okay. So, your satellite is going in this orbit. So, this I have shown you earlier. I have shown you the same thing by drawing this figure. This is x, y and z. So, this is half of the orbit we are showing, and then I named it this as the n prime and this point as n, this as O. Then we indicated one point as P here, which is the perigee, and then the satellite was located somewhere here. We have written this as S, this is the perigee, and here this is satellite. This angle we have written as small omega, and this angle as theta. So, small omega is the argument of perigee and theta is the true anomaly, already we have written, and then this angle we have shown as capital omega, which is the nodal angle, and then inclination of this orbit with the xy plane. So, we can show projection of this orbit on the xy plane like this. Say, if I show it like this. So, this is the projection of the orbit with the xy plane. So, if you see it from the side, okay, so the orbit will appear like this. If you see from the side, so the side view of the orbit, it is looking like this, and the xy plane will look like this. So, this is your xy plane and this is the orbit. So, this angle here, this is I, and equally what we can say that this perpendicular to this orbit, which is given by this line, in which direction the h vector is directed, okay, this angle is also I, because here if two things are just coinciding and then thereafter you two lines are coinciding and thereafter you rotate it by I angle, and if there is a perpendicular here, this is 90 degree. So, this perpendicular will also rotate like this. Okay. So, how much it will rotate with the vertical? This will rotate by I. So, the same thing is shown here. So, this is your inclination angle, and here it is not very clear, but this is also the angle of inclination, means this is the dotted blue line is the projection of the orbit on the xy plane. So, with respect to this, so this is basically your dotted blue line, this is the dotted blue line. So, with respect to this, the solid line, the whatever the angle it is making, that we are writing as I, which is the angle of inclination. So, we have identified here 4 parameters, and A and E already we have determined. So, we need to work out rest of them. Okay, so, we start at this point discussing about this whole thing. So, in the little bit more explanation, on the earth you may launch your satellite, say here in the case the Sriharikota is located somewhere here, this is the equator, and from the equator it is located somewhere here. So, from this place the satellite is being injected into the orbit, and this orbit then once it is injected, so this orbit will look like this. It will go around the earth, and once it is a launch, so basically this constitutes one elliptical orbit. So, let us say that the perigee line or the periapsis of this orbit, it lies here. So, that means we measure theta from this position as we have shown here. So, this is your perigee line. Okay. So, from perigee line we are measuring this theta. So, from here this theta is being measured. Okay. So, this is your true anomaly. So, this is one of the parameter that we need to determine. The rest others are capital omega. So, capital omega is what we have already written as the nodal angle, and n prime n, this is called nodal line. So, your satellite is here injected in this place, okay, and then the satellite will move along this orbit, but this orbit need not be circular. It depending on the initial injection velocity, it may be highly elliptical or it may be elliptical, but it is never the circular is achieved. So, basically the injection altitude. So, if I show this as the earth, okay, and earth radius is around 6,400 kilometers roughly, and 6,374 kilometers. So, if you look for the satellite orbit. So, it will look 300 kilometers something like this. Okay, it is quite close to the earth surface. If you look from outside the earth, so it will look like this. So, it is going so close to the earth. Okay. And thereafter, if you are looking for the geostationary satellite, so you are aware of that the geostationary satellite altitude is around 36,000 kilometer from the surface of the earth. So, approximately 42,000 kilometer. We have 36,000 kilometers and plus 6,400. This is the radius of the earth. So, this makes it 4 to, so 42,400 it is coming. So, from the center of the earth, the geostationary orbit, it is located at quite far distance. This is 6. So, if we look to the scale, this will be far away. Okay. This will be something like going like this, it is a far away. Okay. But we show that let us say that this is your geostationary orbit. And this geostationary orbit, in this case, this will be in equatorial plane of earth, not in the inertial xy plane. Okay, because the equatorial plane of the earth and inertial xy plane, they differ, they are not the same. So, if you have to reach to this altitude, then at the perigee location, first you would start, let us say this is the perigee location here in this place, or also I will show it here that this is the perigee location. So, from here the satellite orbit is raised, okay, by giving a number of impulses, and ultimately while it is raised. So, this part will approach the geostationary orbit. Thereafter, from here if the impulse is given, so this will be raised. So, initially say this distance is 300 kilometers. So, this distance will also be raised, and on this side this will go to the total from the this place to this place, this will go to 36,000 kilometers, and from here also from this place to this place, from the surface of the earth to this place, this will go to 36,000 kilometers. So, both way it will be raised, so that the orbit becomes circular and in the plane of the in the equatorial plane. Okay, so, this is the basic thing involved in the satellite launching, and if it is polar satellite, so you launch it in the polar orbit, not in this this equatorial orbit. So, we will discuss during course of time. So, let us start with first whatever the parameters remaining, we work it out. Okay. So, there are two approaches for working out the parameters of two approaches. For finding the orbital parameters. The first one is the scalar approach, and the second one is a vector approach. So, we will look into both of them, both are useful. Okay, so, as we were discussing here, so initially once the satellite is injected into the orbit, so which is shown here by the black line. So, this velocity may be here in this direction. Okay. So, inertial navigation system that gives you initial v and initial r, that means x 0 I cap plus y 0 j cap plus z 0 k cap, this is known. and sorry, this is x dot, y dot, z dot, and r equal to x 0 I cap, y 0 j cap, and z 0 k cap. So, in this format the initial velocity will be known. Okay. If this is known, so then you can find out the orbit. So, the problem statement is given x 0 and v 0, which is basically 3 components here, and here also 3 components. Find A E I capital omega, small omega, and theta. So, this is the objective. So, out of that already we have discussed about the A and E, okay. Rest we have to work out. Now, one thing I would like to remind that it may happen that these things are not available. Okay. So, in that case what is available, like if the India is launching its satellite, this is the equator and somewhere Harikota is here, and say it is a polar satellite is being launched, okay, or any other satellite, and it is injected into the orbit. So, from the ground station a radar is continuously monitoring the distance. So, on the surface of the earth at this point one reference frame will be fixed. I would better represent it like this. So, toward the north, toward this is east, this is north. Okay. And so, depending on the direction we are choosing. So, in the case of the satellite we choose it upward, the z direction. So, if you are writing this as the x, this as y, okay, so this becomes z, and this is called the topocentric reference frame. Topocentric reference frame, which is a matter of discussion which will take up later on. Okay. So, while the satellite is launched and it is going into the orbit, so radar is monitoring this distance from here to here, okay. And this distance, this is written as rho. Rho is called range, and rho dot, the rate of change of the range, is called the range rate. So, this is measured. Okay. Now, angles are also measured, which we call as the those things we are going to take later on, because then we will not be able to cover it so fast, just giving you initial idea. So, this is from one station for another station also. So, this is from one station, from the second station also this rho and rho dot will be available to you. So, using this data, then you have to determine this orbit where A E small I capital omega small omega and theta. Okay. So, this we this is called the POD, preliminary orbit determination. So, it is not necessary that this is available to you, just based on this rho and rho dot from 3 stations, 3 ground stations, you will be able to work out. So, if your radar stations are located over India in 3 different places and satellite is visible. So, using initial 2 minutes observational data, 2 minutes, 3 minutes or more. So, there are 2 things, 2 terms we are using. One is POD, which is preliminary orbit determination, and another one is GOD, this is called the general orbit determination. General orbit determination. So, in the GOD a precise orbit is determined using the least squares method or whatever it may be. Okay. In the GOD, precise orbit determination, and POD is not so precise, but it is a good enough, so that you can in the future you can keep tracking the spacecraft, otherwise the spacecraft may get lost in the space. So, now the initial value, your inertial navigation system that gives, it is not precise. Okay. It may be like you intend to put your satellite say here in this place, but your satellite may not be placed here in that place, but it is rather placed in the basket. Okay. And it will have certain amount of uncertainty. So, in this basket, then initial location is given to you, and those location can be used, and along with this data. So, this is the just initial value given here, and along with this data rho dot to refine the orbit and do it to a refine it to a extent, so that you can track it near future, and thereafter you for your actual purpose then you refine it and make it more precise. So, this we call as the general orbit determination, that part. Okay, so, we start with this introduction, we start with our discussion. So, given this r equal to x 0 E 1 cap. So, instead of using I j k, I will be using E 1 E 2 E 3 x 0 y 0 E 2 cap and z 0 E 3 cap. So, this is the initial point, and let us assume that this is given precisely. So, this part is given precisely. In that case, we will be able to determine the orbit. So, we start writing h equal to r 0 cross v 0. If we take the cross product here, okay. So, we can write here E 1 cap, E 2 cap, E 3 cap and x 0, y 0, z 0, x 0 dot E 1 cap times y 0 times z 0 dot plus E 2 cap times E 3 cap x 0 z 0 dot minus okay. So, this gives you h. So, h will have 3 components h 1 E 1 cap plus h 2 E 2 cap and this quantity is given here. So, h 1 you can write as y 0 z 0 dot minus So, these are the three components of the angular velocity per unit mass. Okay. Now, we also we can write H as say here this is the earth and one satellite has been injected and say this is the injection point. This angle we show as theta. So, this is the perigee line, theta is not known. This angle we will write as alpha, and here we will draw one line which is perpendicular to this, the radius vector. This is your r vector, from here to here this is your r vector. So, this is 90 degree and this angle we will write as beta. So, beta we call as the flight path angle. So, alpha is your angle and this red vector which is appearing here, this is nothing but your. So, beta I will remove it here, and first let me write here this red vector is nothing but your v vector v 0, okay, and this is here r 0, and this angle this angle is beta, which we are calling as the flight path angle. So, if you see the angle between the r vector and the v vector, r vector is like this and your v vector is here in this direction, this angle is alpha, okay, and this is going toward the center of the earth. Center of the earth. So, r cross v, angle between them is sin alpha. So, we write here r 0 v 0 sin alpha. So, H is also you can notice that v 0 cos alpha, this can be written as r dot, which is the radial component, in this direction the velocity component, and in this direction the velocity component. So, along this direction r dot and here r times theta dot. V 0 sin alpha. So, these are the two components. So, this is the radial component and this is v theta component, and we will number them as, let us say initially we have not written anything. So, we will number them as 1, this as 2, and then we also use the equation r equal to L by 1 plus e cos theta, because this is the conic section equation. So, we will use this. Okay. This information we have, and then other part we have already written here, this part. So, this equation maybe we can write as 1 and here this we can write as 2. In this place we can write this as 3, this has 4, 5 and this has 6. Okay. From here this equation can be reduced in this format. Minus E theta into theta dot. Okay. Okay. What we are trying to do here, see, we need to determine this theta. This is one of the objective, what this is, this quantity is. So, I have to determine this A and E we have already worked out, okay. And small omega, capital omega, all those things we need to work out. Okay. So, this is one part, and then also cos alpha we can define as and if we do that. So, R 0 V 0 cos alpha, this we can write as x 0 E 1 cap, y 0 E 2 cap dot product with x dot 0 E 1 cap plus y 0 dot E 2 cap plus z 0 dot E 3 cap. Okay. So, R 0 V 0 cos alpha, this becomes y 0 dot plus z 0 dot, and therefore, cos alpha from this place is x 0 dot plus y 0 dot plus divided by R 0 V 0. Okay. So, if your position is given in this format, so you can see that immediately you can work out alpha. This equation is there and this equation is there. So, you can determine alpha. So, we will discuss about this, what is the significance of doing like this. So, this is 6th and this we will number as 6 7, okay. And this will number as, in the next step we will do it, or we will do this part on the next page. So, this equation can be rearranged at E sin theta equal to this minus sign cancels out. So, E sin theta this equal to L by R square R dot L by R square R dot, and then from here this theta dot. Minus sign that gets cancelled. Okay. And R square theta dot, this quantity is h. So, this we can write this as already we have derived for the central force motion, R square theta dot equal to h. So, we can use it here and get this equation. So, we have got E sin theta equal to L times R dot divided by h, and so this can be written as L by h. Okay. some more manipulation can be done. Actually, what we are trying to do, we are trying to express everything in terms of r 0, v 0 and alpha. So, we can reduce this part. R dot you are already aware of r dot we have written here, this is your r dot. So, we can use it. So, r dot is v 0 cos alpha. So, r dot is v 0 cos alpha, and what this, there is some relationship between h and L and h. So, we know that h square equal to mu times L. Okay. And if we want to remove this L, so L becomes h square divided by mu, and we can insert here, okay, or simply we could have written here L by h equal to h by mu. Okay, so L by h is there, so h by mu we can remove this h by mu. And also we know, so this we are getting from using equation 4, from 4, and then h is also known to us, and h we have written in the equation 3 r 0 v 0 sin alpha. So, r 0 v 0 sin alpha v 0 cos alpha divided by mu. This is from 3. So, E sin theta, then this gets reduced to r 0 v 0 square sin alpha times cos alpha divided by mu. So, this will number again, this is 7, equation number 8. And suppose we have the another expression for E cos theta. So, definitely we will be able to find out theta from this place. E sin theta and E cos theta is there. So, we can eliminate, here we have the alpha is known, r 0 is known, v 0 is known, mu is known. Okay. And if we also got E cos theta, so we can eliminate E and we can get in terms of sin theta cos theta. So, it will be solved for theta in this case. Okay. So, we have finally got this. Now, L by, already we have written r equal to L by 1 plus E cos theta. So, this implies 1 plus E cos theta equal to L by r. Okay. And from here E cos theta equal to L by r minus 1. So, therefore, E cos theta, now L equal to, if we want to express in terms of mu and other things. So, we can do that. So, mu times L, this equal to h square, and therefore, L will be h square divided by mu. Okay. So, this becomes h square divided by mu r minus 1, and h we are aware of how much this is r 0 v 0 sin alpha. So, this will be whole square divided by mu r 0, okay, minus 1. So, this gives us E cos theta equal to r 0 square v 0 square sin square alpha divided by mu r 0 minus 1 mu minus 1. So, finally, we have E cos theta equal to r 0 v 0 square sin square alpha divided by mu minus 1. So, here we have got one expression E sin theta, and here we are getting E cos theta, all in terms of alpha, r 0 and v 0. So, this is equation number 9, written 9. Okay. And in both places you will see that r 0 v 0 sin square alpha is there, and here r 0 v 0 square sin alpha times cos alpha. So, suppose I write this as E sin theta equal to r 0 v 0 square sin alpha times cos alpha and divided by mu in this way, and the quantity in the bracket I write as A. So, this becomes A cos alpha. Okay. This is for just giving it a brief notation, and this also can be reduced then in this format. So, this will be A sin alpha minus 1, and therefore, E sin theta divided by E cos theta, that becomes tan theta, and we get this as A cos alpha divided by A sin alpha minus 1. Now, the question is whether using this equation you can, using this expression, is it possible to determine theta. You see here in the, if this is the orbit and r is always measured from the focus, okay, and this is theta. So, as the satellite is going around in the orbit, so theta varies between 0 and 360 degree. So, if you do only using this equation, so you will have problem that whatever the value you are getting, so where it is lying, it is lying between the this quadrant, this quadrant, this quadrant or this quadrant, it is between 0 to 360 degree, okay, and you know that they will repeat their value. Okay. So, that is resolved using the sign of theta, sin theta sign, because E is always positive, okay. E is always greater than 0, always positive, it will be 0 only for the circle case. Okay. So, therefore, we look for the sin theta sign of this and cos theta sign, whether it is a positive or negative. So, sin theta is positive here, sin theta is positive and cos theta is also positive, sin theta is positive here and cos is negative here on this side, here sin is negative and cos is also negative, in this portion sin is negative and cos is positive. So, if you know what is the sin theta and the cos theta value, so using this table you will be able to say in which quadrant the theta is lying. That means, you will be able to determine the exact value of theta, the right value of theta. Okay, sin cosine they are repeating their value, say the sin 45 degree, this is 1 by root 2. That means, you are starting with this, you are going like this. So, sin theta is 0 here, also this is 0 here. So, at theta equal to 0, 180 equal to 0, this is 0, again it will be 0 here. Okay. So, till 360 degree it is a repeating the same value 45. So, 1 by root 2, 1 by root 2, suppose it lies here. So, again it will lie here, means it between 90 and 180 again it will lie. Okay. Again on this side if you go, so this becomes negative. So, there is a repetition. So, we have to resolve that, but here if you look the cos here between 90 and 180, in this range the cos becomes negative. So, this way you will be able to resolve. So, we will discuss further on that once we take the vector notation. So, how to resolve the sign, that we will discuss. So, this way we have been able to here find out one of the parameter which is theta. So, right now we are in a position where we have already determined A, E and theta. So, these are the three parameters determined. And rest three parameters we have to work out. So, we stop here and then we will continue in the next lecture. Thank you for listening.